Alright, so this question is talking about protons colliding. We've got a proton of mass m colliding obliquely with another proton. So basically that means that here's one proton, here's the other proton. He's going to hit, but he's not going to hit straight. He's hitting at an angle like a pool ball that you want to go down this way. So he's moving at a speed of 6 million meters per second. That's pretty quick. And the second one's stationary. Assuming the collision is perfectly elastic, so we didn't lose any kinetic energy, and using the fact that the first proton is moved 30 degrees from its initial path. So its initial path's going this way, it hits this guy, and it moves off on a new path at 30 degrees from its original path. Let's call this guy 1, this guy 2. Here goes 1. He's gone. What you need to know to solve this problem is that if you have two objects of equal mass and they hit obliquely, this can help you with your pool game, except that the white ball is not exactly the same mass, so you have to adjust a bit. They will depart from each other at an angle of 90 degrees. I can show you a fet.colorado.edu simulation you could play with to have a look at that. So this guy is going to move off at an angle so that this angle is 90 degrees. What angle is this? Well, 90 minus 30, we go 90 minus 30 equals 60 degrees. So this guy's moving off at an angle of 60 degrees. We're supposed to figure out the speed and direction of each proton after the collision. Now, here's a nice fun fact that can help you through these questions as well. When you're dealing with objects of the same mass, then you can ignore that mass because velocity also is a vector quantity. So when we've got a situation like this, where I have a proton hitting another proton, they're the same mass, I don't need to find momentum. I just need to use their velocities. And what I need to recognize is that this is the total momentum or velocity that exists in the equation because this guy was stationary to start with. So when I construct my diagram, I can just take this arrow and move it up that way, right? So that this 60 degrees is on the opposite side of this line, so that's 60 degrees. This right angle slides right up so that that's a right angle, and now I have a right triangle with the hypotenuse being 6 million. So I'm just going to reconstruct that triangle down here so that I can write the values in on it. So here I've got my 90 degree angle, here I've got 60 degrees, and this is my hypotenuse, here's my 30 degrees. Remembering that this one is the 1 ball, this one is the 2 ball, and this was the initial total amount. So I've got 6.0 times 10 to the 6 meters per second on this side, so my hypotenuse. Right, so I want to set this up. I can solve it a number of ways. I like sine. So my hypotenuse is here. I want to solve for this side. I'm going to use, that's my opposite side to the 30 degrees. So sine is opposite over hypotenuse. So this guy can be my opposite side. I'm looking for my opposite, so I'm going to go sine of the angle times hypotenuse. So sine of 30 times 6 million. And I just happen to know that sine of 30 degrees is 0.5. So that's going to be 0.5 times 6 million. So it's going to be 3 million meters per second on this side. So number 2 is going at 3 million meters per second. Now 60, this is the other one. And if you wanted to, you could go c squared minus a squared equals b squared at this point. I mean, if you've got simpler numbers, it could help. A right angle triangle can be solved a number of ways. But if I wanted to do this same thing, make this my angle of interest now, and I want to solve 1, then that's sine again. So now it's going to be sine of 60 degrees times 6 E6, if you want to use your calculator that way. And not as familiar with sine of 60. So I'm going to cheat and look up the answers in the answer key, but you should be able to plug it into your calculator and find it. And this one looks like 5.2 times 10 to the 6th. So when I solve this out, it should give me 5.2 times 10 to the 6th meters per second. And for direction, you would say that this is ball 1 is 5.2 times 10 to the 6 meters per second, 30 degrees from the incident. So the incident angle is the one coming in. And this one is 60 degrees. You could even say above and below if you want it to be really specific. But you just need to make sure that you understand whatever words you choose are describing what you're seeing on the page.